Now, we've mentioned that there's a very important relation from advanced classical mechanics. And that relation says that the velocity of a particle is always equal to the partial derivative of the Hamiltonian of the particle with respect to the momentum. But I don't want you to just take this from me on faith. Let's actually give a proof of this. And for that, we're going to give you a little mini, this is a little kind of aside, but it's a mini crash course in advanced mechanics. Advanced classical mechanics. Now, I'm really just going to focus on deriving this equation. Now, this equation is one of two equations that Hamilton derived for the Hamiltonian. So we might call this Hamilton's equation, number one. So we're going to try to derive this. Now, it's very interesting, I think, the derivation, because it shows you why, in fact, even in classical physics, excuse me, even in classical physics, why it's so important to write the energy in terms of the momentum. Ultimately, that's because both energy and momentum are conserved, and we can use these great conservation principles of physics to, in fact, prove this very beautiful relationship. So here's how that proof would go. Let's imagine I've got my particle, and he's moving around. Now, I'm only going to prove this for a free particle with no potential energy. On your assignments, you will have the opportunity to actually do the more general proof. But let's just focus on the free particle. So the trick in proving Hamilton's equation, the trick that we're going to use is we're going to apply a tiny test force onto our system. So I'm going to call it F external because it's a tiny little external force. And the idea is I want this to be so small that it doesn't affect the trajectory of my particle at all. And it's important that this test force is going to be small, right, so that what I'm learning about is the actual trajectory of the particle. So I'll learn about what the particle actually obeys. But it has to be non-zero. You'll see a little bit later on why it has to be non-zero. But it has to be non-zero so that by applying it, I actually learn something. So I apply that. And then I now apply some conservation laws. I know, for example, when I apply this external force, right, the total energy of my system will no longer stay constant, right? It's going to change because my force is doing work on my particle. But the law of conservation of energy says, well, the change in energy of the system has to be matched by how much work I'm putting in there. So the change in energy of the system, therefore, has to be the power that I'm putting in. And the power I'm putting in has the famous formula that it's the external force I'm applying times the velocity of the point on which I'm applying that force. But I'm going to apply this tiny test force to my particle. And when I apply it to my particle, that means the velocity of the contact point is just moving along with the particle, and that particle is moving along with a speed, which we can get from the trajectory. It's just the x dot, right, from the trajectory. So far, I've just applied conservation of energy. And, I've learned something interesting about the energy my external force is pumping into my particle as he follows his trajectory. Now, let's connect this to the Hamiltonian. This is where things get interesting. So the total energy is actually the same as the Hamiltonian of the system. But the Hamiltonian is written in terms of the momentum, and it's the momentum of the system that's changing in time. And now you can see why this functional dependence is important. This will only work if h is written in terms of p. So if I take this derivative, right, now I'm going to do some math. So this connection was just the definition of h. Now, the mathematics I have to do is, okay, it's chain rule. I need the derivative of h with respect to its insides. So that gives me dh dp. And notice right now, I'm writing that as a partial derivative, even though it looks like h is just a function of p. The reason for that is that later on, right, when you include potentials, then the Hamiltonian does depend upon the potential energy of where the particle is. It will depend upon p and the location x. And that's something you'll work through on your assignment. But here, we just happen to have just one of the variables involved. So I take that time derivative, I get my partial dH dp, but then that has to multiply the derivative of the inside function, which is p, right? So then I have dp dt. Now, dp dt is talking about the change of the momentum of my particle. Now, my particle, of course, would never have its momentum changing, right? Because momentum's conserved, right? Unless I were applying this external force, right? And the external force is actually the entity by which momentum is pumped into my system at a rate where dp dt equals the external force. That's how we account for conservation of momentum. So this is dH dp times then my external force. And that comes about because these two are equal. And that is another manifestation of conservation of momentum. Just like here, right, energy is conserved, but that's the total energy of both whatever's creating the external force and the particle. The particle's energy is changing, and the external force is doing work, so conservation of energy looks like a time derivative formula, where power is what represents the rate at which energy is pumped into the system. Similarly, here, the momentum of the system is changing because I'm applying my external force, and as a consequence then, the time derivative of that momentum, the rate of change of it, is actually my force. Now, if you're not familiar with that, another way people often write that is they say, well, the total external force on a system, right? Frequently they say that's equal to the mass of the system times the acceleration, d by dt squared, of the center of mass of the system. So you can call this x, the center of mass of my system, right? Which is, of course, just saying, another way of saying F equals ma. But in my case, I only have a single particle. Now, the next thing I want to notice, I guess, or better to say, is I could write then the force as the time derivative of the mass of my system times then the velocity of the center of mass, right? One time derivative is out here. The other time derivative is d by dt of the position of the center of mass is the velocity of the center of mass. And of course, the total mass of the system times the velocity of its center of mass, that actually is the total momentum in my system. So that's one way you could understand the origin of that relation. Now, the final observation is, let's look at what this chain of logic is telling us. Notice we can now equate the left-hand side with the right-hand side. So we learn that dH dp times the external force actually equals the external force times x dot. And as long as my external force isn't zero, it just has to be tiny, so it isn't disturbing how the particle's moving. But as long as it isn't zero, I can cancel it from both sides of my equation, and I now have proved, in fact, Hamilton's first equation, which we depended upon in order to come to the conclusion regarding how the frequency of our particles have to line up with the classical Hamiltonian.